Thanks for having me here. Just myself, I'm trained as an architect, kind of like everyone here in this room. I went to RISD, so I'm an East Coast guy. And, at RISD was really kind of focused in process and a lot of, at that time, a lot of interest in material phenomenology. And a lot of us kind of struggled to have buildings at the end, but that was always really important process and kind of research. And at that time, and also with your professors, when we were coming up, I think we had just come out of a period when people stopped talking about architecture as far as styles, right? We grew up in the 80s, and at that time they were still doing postmodernism, right? Which was like a big reaction against, say, modernism and most specifically brutalism. Kind of this amped up, as far as you can take the grid and modernism, complexity, right, with that language of the grid. And people were like, this is horrible. Let's go back to pitch gables and really graphic. So I think, I moved through a whole period. And during that time in school, I looked to the West Coast. I was like, wow, what are these guys doing? So we're talking about people like Frank Gehry, Tom Main, who founded Morphosis, Eric Owen Moss, people like this that were really kind of challenging the idea of what architecture was, and so far as going maybe political, but maybe definitely this spirit in deconstructivist kind of thought of just challenging things. Why are things the way they are? I think that's a really good sort of backbone to interrogative design, right? Kind of questioning things. So I think that's important because this is one of Tom's, I think, in his last 10 years of sort of contribution in architecture. Federal buildings in San Francisco and Caltrans here were big projects. And this was the first museum that he had done and designed. And I had the privilege of working on the enclosures, from a very early point on with the team through materials research. So, yeah, I think that's just a preface to this. Good to know that, Southern California is a hotbed of thought, and you guys have a blank canvas ahead of you. This presentation, I'll just go through some basic facade design considerations, right, and facade systems. I think it's important to think about architecture and design, but we work in the language of construction, right? And in the end, everything that it takes to get these sort of things built that accommodate all the considerations. A lot of times these are like constraints, right? Like site constraints, but there might things to do with environment or performance. And in the design, you try to find the sort of alignment of all these things. So moving on, we'll talk about the control surface geometry, and you'll see how this in the deep dive, how we sort of move through a lot of these kind of issues and challenges. And then we'll have some time for Q&A at the end. Let's get going. I guess let me get this guy out here. All right, so facade design considerations. So obviously there's a lot of environmental factors, right? So wind, funny enough for enclosures, and this talk is really focused on high performance enclosure design. Wind is actually one of the biggest sort of forces that we'll design to. Water, number one cause for failures. Water is big time enemy for detailing and kind of how things go together. Systems, we'll talk about systems of construction. Interface, this is where we have problems typically. Seismic, right? That's a bigger sort of movement concern than wind even. And if you're working locally here or some places in the world, seismic's a big deal. So that might be driving a lot of considerations. Solar, so obviously, right, everything to do with energy consumption, how we choose our coatings for glass, where we have opacity, where we don't. These are things that we always have to consider as we're sort of designing. And then we move into sort of things that are more specific to the building, right? Is it a floor-to-floor thing? Are there multiple floors? This influences how we're going to actually wrap the building, These things actually have to be supported And a lot of times we go to the floors, but sometimes there are no floors. And this building is a great example. We'll see some of that. Building deflections. So with the wind and the forces, these buildings move, right? Everything moves. Way early in design, I know specifically for a good year ahead of even this thing, getting to construction documentation, we were making sure that this classroom, which is kind of cantilevered in space, actually didn't move very much. And the reason being that curtain wall in between that long bar and this little space here, we knew that if it moved a lot in seismic, we'd get a lot of joints, right? So like, these are kind of things that all factor into, I think, in the end, the final aesthetics, right? And continuity of joints, or is that important? Is it not? Do you want to play with the joints? So, once again, constraints and how they can influence design. Building maintenance, you have to take care of your building, actually. How are you going to clean the glass or replace any panel in the building at any given time? And funny enough, if you figure this out, you probably figured out how you're going to install it as well. And building form, like how complex is it? That's going to impact how you actually are able to install and maintain things, as said. And then, into specifics further, right? Manufacturing, all right? Like, what are we saying? Okay, we like metal, or we like GFRC, glass fiber reinforced concrete, or we like precast, whatever it may be. All these materials have properties, right? And they also come with like a certain kind of limit to how they're made. Right? If the thing, say, is metal, and it's a metal panel, well, you're going to be constrained by how it gets to the shop, right? Which is probably a coil. We know it's 5 foot wide. These kind of things, right? Tolerances, how tight are they being made there? And actually, how tight are things being installed? And actually, you have incredible amount of design power just through this little book of specifications, because at the end of the day, you can miss a lot of stuff in drawings, but if you have in specs, you'll actually have some bargaining chips. Anyway, that's for way late in career, but leverage that at some point. Installation, once again, it's critical just how these things get installed. That's gonna really dictate if it's gonna be in budget, this, that, whatever. Weathering performance, right? Geometry. Is there stuff where things are naturally not draining well? Is there stuff that's kind of taking a lot of wind load? And then we always have to look through moisture control, thermal, and insulative qualities. Are there shading devices? Durability. So these are all kind of things that we have to think about. And I think at times some of these become larger constraints than others, but then those become sort of opportunities, I think, also in sort of pushing a decision. So facade systems, real quick before we get into this deep dive. We talk about like enclosures, and let's split it up into opaque and sort of glazed assemblies, right? So if you look at an opaque wall, you might have like a stucco wall there that you see as a barrier system. This means that like that skin is actually where all the waterproofing happens. And anything past that is like a backup, but that's pretty much it. Cavity wall, brick walls are a good example, right? And traditional ways, you actually have two widths of the brick stacks that are actually creating a sort of cavity. The outer taking, a lot of the weathering. Once again, I think there is some ability to have some drainage behind there, but the face is essentially taking most of the weathering. Any water behind there is just meant to be drained. It's ancillary. Rain screen systems. This is the modern stuff, right? Everything on this building is a rain screen. You basically start with a waterproofed wall, and then you can, any number of materials, metals, terracotta, GFRC, the list goes on, can be attached to this wall as a sort of aesthetic and an initial weathering barrier. So some diagrams of the different types of wall systems. You can see, basically like someone's actually indicating here positive and negative, right? That's also pressures. So we're actually looking at pressure equalizing systems and how that can be detrimental to moving water. Or just plain failures, right? So, we have some details, and without getting into it all, this is like an exploded. Here, the backup wall is a simple CMU wall. You see the insulation in blue. Those little vertical girts are just essentially spacing out, creating this cavity for the insulation, which also is what you're able to screw into for a substrate, which is just a board of some sort, probably fiberglass board or plywood, and they go and waterproof this in subsequent layers. So in all of this, if you look at any of these diagrams, you have the finished face, thermal, moisture line. And the notion is that these things are continuous, right? So there's something called a pen test, right? Where if you take your pencil on a detail and you run it along, there should be continuity through all of this. And so the yellow is like this finish face, right? Which is the aesthetic. It's actually the outermost face. And this is important because this correlates to kind of your design surface. Say you're doing a rhino model, right? That's probably what that surface is. So as you go through the process, that surface starts to have a lot more drilled in sort of specificity and kind of accountability to that, both in form and what works for the detail, right? So the thermal line, you can see it's behind the blue, and at the glass, it always comes together, right? Because the glass is essentially the aluminum frame where you get some sort of thermal loss. But the glass in and of itself, with the insulated glass unit, provides all of the three sort of functions there. So you'll see that in the diagrams. Where at the glazing, everything kind of joins up. Cavity wall, you see how there's a cavity. There's actually some plus and minus pressure going on inside there, but the skin is so robust that you can kind of take that. Real similar kind of mentality to the barrier, but you have that cavity, right? And then here are the rain screen. You can see how everything's much more lightweight. The components are going in are very prefabricated in a sense, right? The whole assembly may not come pre-assembled, but we're talking about components that come from a shop. And so here's some examples, right? You can take any number of materials and using girts, which are these horizontal, continuous little Z-clips or hat channels. We call them girts, just basically holding off the panel to create that airspace. And then sometimes just intermittent brackets. And you'll see how this can get quite complex. But the idea here is that, all these examples, some of them really complex, right? And that's easy to understand, right? Upper left, it's a tiled assembly, right? Pretty simple. And then you can get it to something like a rain screen here that's actually terracotta and 3D formed, right? Cast. Here it's interesting that using that material, they're able to cast it in a way that if you try to deform metal like that, that'd be exorbitantly expensive, right? So there are these things that materials kind of inform about what you're going to do. So last little bit here with the punch windows. Everyone knows what those are, right? Just basically a window that you have in a house would be a good example. It comes with a continuous frame and it sets inside an opening. Storefronts, basically, they're typically along like the ground level of a building. Window walls, essentially like a storefront. They're framed in between slabs, but there might be this sort of like a Lego effect of component sort of interlocking that happens horizontally. And then curtain walls, right? This is what you see on a lot of towers. Here, the example with floor-to-floor glass, but essentially these panels coming with the frames already on them, lifted into place and hung off of slabs. So, with materials and systems, you're implying a certain sort of way of support. So you see these little up and down arrows are kind of like where movements are happening, right? And the reason why that's happening in the three here on the left is essentially, actually the two on the right, have floors. So this is like mid-story in a building, and the slabs are kind of going in and out. So there's all these kind of considerations when you're doing these things. Once again, the glazing is where a lot of these lines of continuity come together. And just knowing your systems and using them as a palette in a sense. If you know the typical assembly of any of these things, you can kind of approach with confidence in designing, just understanding offsets, the sort of depths that you need for the structure and whatnot. And once again, you can permutate this stuff, right? So the bottom two here, the one in the middle with the bottom middle storefront window wall, those are double curved pieces of glass that are based off of cylinders, right? And so actually not double curved, single curved cylinders were the base geometry, and they're point supported, but it's essentially a storefront, right? Plus it's leaning out, so it's pretty complex. Here on the curtain wall, there's actually like, you know, this bottom right image, there's actually 5 means of support for this sort of curtain wall as it goes up. You can see kind of on the right of the image, there's actually no floors there where you had to have steel, which mimics sort of floors. And, you know, why mimic floors? Well, the skin was meant to be continuous, and that sort of informs this sort of logic of, okay, well, that's where we need support. So, like, I think there's a lot of, like, interconnectedness, right? If you think about technical design and what it takes to deliver something. And a lot of this is based on a systems-based approach, right? So everything we talked about, systems, glazing systems, opaque wall assembly systems, pretty soon, you know, like what is that coming from? Well, it's coming from like a manufacturing logic, right? Of like way back in the day, the assembly line, like Henry Ford, all this sort of thing, interchangeable parts, the assembly line, and then super duper, you know, like this is all within like, you know, within our lifetime, this kind of move into fully digital, right? This is like the Boeing 777, which is like fully digital. They use CATIA. There was no paper, so to speak, right? High level of definition of detail in the model down to like the threads on the screw. So like technology, right? Like what is it now? It's enabling us to do so much and push that into a lot of things. And I think you know some of the constructs that you guys made, right? The notion of taking digital fabrication sort of logic and that design data set becoming an engine for driving all sorts of things like analysis and fabrication and all this sort of thing. So this is a quintessential project, the Venice house, 2468 house that Morphosis had done, all hand-drawn. This was actually the first set of construction drawings that the office had done, like in theory, as this building was built, let's say out of built projects. And they even questioned, right, the notion of what you know, this does not look like the flat sort of plan section and typical sort of layout, but really, you know, getting into the constructability in a different way and talking about the building as far as breaking it down, as far as like parts, holes, talking about things in terms of assemblies, right? So, you know, like we talk about things with the material intent, but that comes with a whole host of sort of constructability constraints. So control geometry, right? Really important. Like what is the base geometry that's driving your thing? And there's no question that we can rationalize pretty much anything. We can optimize things with unlimited cost, with technology and rapid fabrication. More and more so, I think like mill time and things like that are not prohibitive. I think like things are becoming much more easy to kind of push fabrication, but at the same time, you have to have restraint. You know, if you start with facet and folded geometries, well, you know that you can probably frame that out in any infinite number of ways because a lot of stock comes as you sort of flat. When you start getting into curved sort of forms, like that one storefront I showed you, rather than taking something that was completely just, oh yeah, this sweep surface, 2-rail sweep looks great, you know, for example. You know, you actually start with something that you know is only single curved, say like a cylinder, and you might tilt that in space, or you might trim it. So like a certain kind of rigor comes from just understanding geometry, right? That if you understand the base geometry of something and understand the limitations of what you're proposing, you pretty much have a large overview of confidence of what you're sort of talking about, right? Twisted, warped geometries. These are ruled surfaces as well, meaning they have can be described with straight lines, at least in one direction, right? And that's a similar thing with these, like the cones and the cylinders and the folded geometries. Is they're developable, right? I mean, you can flatten them down onto a flattened surface. Whereas things like double curve geometries, you cannot, right? So you got to think about materials that are, say, moldable, or if you're doing metals, to have the money to deform the metal. So like these kind of things, you know, in the end of the day, you might have a finished panel that can do whatever it wants, but you have to somehow support it, right? So the notion of geometry, setting out, right? You start setting out rules, you know, with this, and like there might be planes that cut through your surface that relate directly to your grid lines, or you start to have datums. So I think you start creating project-specific setouts and work points, right? You'll see in the details, we have these little work points, and you'll see how those become important. So here we are in Costa Mesa. As I said, this was the office's first fine arts museum. And, you know, this is actually an early rendering in concept. I mean, quite a you know, clear kind of understanding about form. Really, I think a lot of it is pretty consistent with what is there now. And in fact, this is maybe a little later rendering where the bench down at the entry is actually detached. But the notion of like challenging what a plaza was, right? This arts complex has an incredible amount of sort of venues going on it, but it didn't have like a real center. And there's that Sarah sculpture out front, and it was thought that the building could have a sort of an elevated plaza, or create a new center, at least the public way to invite the public in and really work with the circulation that already existed. So the notion of like, you know, the Sarah connector and conceptually that inflecting into some of the form. The notion of the plaza, you know, at one point, as I said, this was even connected, you know, this whole plaza went all the way up, but now it becomes more of a formal gesture, more so due to strategics, due to code and fire egress is why that's not connected. But, you know, conceptually, right, like diagramming this out in a really clear kind of set of images based off of really the design geometry, you know, the same geometry we're using to drive like construction and whatnot. But in any event, the idea of like an elevated green space, you know, to really heighten the experience up there on the plaza. And then here this image which kind of shows a terracotta facade, which we'll kind of deep dive into. So yeah, and the other hallmark, I think that the trademark of this is this sort of submerged or suppressed gallery space below the plaza. The whole roof of that, you'll see pictures later on, is basically a concrete slab that's waterproof like a bathtub. So it's the most robust sort of waterproofing method using hot rubberized asphalt. It's actually almost like a medieval technique. It's like hot tar, right? But this will never leak. And, you know, you can kind of see here along the bottom here, that sort of window gallery, as it called it, that you could view art from. And so from early on, you could see really the notion of continuity and this sort of material, which at the time we didn't know that it was going to be terracotta. You know, we had thought about materials such as GFRC, which is glass fiber reinforced concrete, which can be sprayed into a mold. Basically, it's similar to concrete, but it really is a composite. That could be easily, you know, achieved or used to achieve these kind of images. But like, you know, I think you pick up from the images that like a lot of this, the ribbon-like quality of this facade actually came into the building. And so I think it was almost like this really celebratory kind of element in the building design itself. Like in most buildings, you have to go through the whole process of like, concept, schematic, where you're really getting the larger sort of site constraints done, and like egress or fire access, all these sort of things, and eventually into sort of, design development, where you really like kind of have the design sort of like locked down as far as form, and you're really developing those systems and the program itself. And eventually CD phase, like this is where we're developing a set, which is essentially construction documentation phase, right? We're creating documents that are essentially like a instruction, right? Manual for the contractor. And they are contractual, because what you say is what you want and what is priced and has to work, So yeah, going through all the plans, the typical plans, these are really great drawings. So look at the wall sections, right? As far as facades, they're usually blown up at a larger scale. You can't escape sort of the way things are intended to be supported or not. And so this is like a very, very like, everything you see here has actually been sized and engineered. So all the W sections in primary steel, all the members, like you can see this middle section is a cut right through the sort of curtain wall there at the door. Everything's been sized at this point for the most part. And really kind of just trying to break down your building in a very simple way. Right? Because like you're going to give this to someone and you're going to say, okay, what's the price? And immediately, if this thing is confusing, you're going to get a high price, And it's about, everything is kind of like drilling through the problems and really documenting your design in a way that, we're not talking about colors. We're not talking about things that are just overtly aesthetic, right? But all this stuff invariably is tied to that in support of the design, but also is sort of an opportunity for creativity in a sense, right? So like a basic rain screen system. Here's a classic system sheet where we have a plan, section, elevation, usually floor to floor, grid to grid, so you get the sense of how things are being supported from a primary steel standpoint to secondary to the actual sort of panelization of the skin itself. And from these, we key off details. Here, we're talking about types of panels too, right? On the left, we're talking about flat panels that are curved and flat, and then flat and curved. And then, so, the long ones, this sort of like kind of cookbook and sort of, description of the base components that go into this. These were kind of special drawings that we did in Kais at Walter P. Moore, and that team there we worked intently with, even to the point of like what this is showing is the steel. Usually in a wall, everyone knows like metal studs, right? That's what would infill all of what you see here. But what we're really saying here in our design contract, our construction documents set by showing the steel is really giving like a kind of strong indication of how we expect this thing to be supported, and why. Because I think what's important is like that was so indicative to how our system would need to work in order to avoid all these new joints that would show up, right? If you look at this building, you really don't pick up anything but like the continuity of the pattern. And that's because all the support behind there was worked out to a point where we actually don't have any expansion joints in this building, which is very, very rare. So anyway, drilling into weeds there, but the document set, we go through every system. So a curtain wall system, plan, section, elevation, right? We give it a number, we go through details. And I think the thing to take away from this is like a plan detail, right? The terracotta rain screen here coming up to the glass. You see this L shape is actually mimicking the T's that are in the middle, but at the end it worked better as an L. You never see the other side of the T. So like all these things kind of, coming together. But at the end of the day, you're taking this face of glass or the face of terracotta, and you're offsetting these things in space, right? And these are directly correlated to details. Where you have like typical details giving these offsets. Everything's been sized. This is eventually what we end up getting back from Roschmann Group, who was the German subcontractor on the glazing that did all the custom steel. So I mean, intrinsically, their stuff is not surprising us, right? But what we're having to do is just contend with variances in their system or whatnot. But really, this gets to the notion of like, that's a very strong part of design intent, is that actual geometry, right? And we even did these like kind of secondary steel diagrams for the sky, the curtain wall in the previous image. This is the skylight that you see right out here. So yeah, a lot of sort of thought going into sort of the setting out and, you know, the sort of rigor of looking at each one of these systems and all the unique conditions. But at the same time, you know, just being very kind of strategic, right? If you do certain things in selection of the system or give certain considerations, you can drive things after a while from a kind of like a digital sort of surface control standpoint, you know, with confidence, because you kind of know what your systems are doing. So yeah, once again, all these details. No irony that the skylight terracotta to glass detail almost looks the same as the plan detail, right? The notion of continuity. Here's a zoom in, so the Roschmann sort of glass design. It was predicated on this rather than structural sealant, which would bond this IGU back here typically to that steel T. What you can see here is an aluminum carrier gasket and aluminum piece that they screw in, that they then take this toggle, which goes in, it's rotated 90, they go in, rotate it in, and then they screw it in. So this gives the same look of the glass, but of being seamless and capless, but it's a completely different system. So it's kind of, you know, it's one of those things where you have to kind of anticipate what things could change, but be very sort of like deliberate about documenting things you want done a certain way. I think in doing that, all the other pieces fall in place more or less. The construction team would always tell you that they wish they had more resolution. But you can see here, and this picture is really good, right? You can see all the girts that are coming on this wall. This is the side of this building here. That's that wall right there. And you see all this black stuff is the waterproofing membrane, right? Here, it doesn't have it on top of it yet. That's the Dens glass, the fiberglass board that's screwed onto the metal studs that are infilling those secondary steel pieces that you saw diagrams for. And you know, at some point, this becomes lowest common denominator, right? This is some guy out there with a 70-pound piece of terracotta trying to get it up, you know, up in the air. So there's a lot of thought to, you know, how this stuff needs to happen. And so I'm going to have to go a little quicker now, but, you know, really the exterior system surface model, each one of these colors is a different system, you know, and really we split up the model to sort of, you know, obviously drive the form, but also the panelization with the center lines. And this was a study looking at, like, you know, the continuity in the joint sizing, right? We had these sort of thicker horizontal joints to emphasize this kind of initial ribboning that we had seen. We went through like costing for metals and GFRC. Ironically, terracotta was cheaper, right? I think it also came from the sense that we had not rationalized the panelization, you know, to a degree that, you know, I think any material would need to be early on. But we saw the legs for terracotta. Glass selection wasn't so daunting. We knew we had to do like certain performance requirements for energy, but through that, you're still picking like aesthetic quality of glass, whether it's maybe one manufacturer is slightly darker or more clear or less green. The quality of sort of like distortion in how those lights of glass are being fabricated. So those kind of things are looked at. And, you know, with terracotta, we got good pricing and we had already done some research. This is at the Advanced Ceramics Assemblies Workshops. actually architectural ceramics assemblies workshop at Boston Valley Terracotta, who was the final subcontractor for this terracotta skin. They sponsored us a workshop where design professionals and even universities would go and basically explore sort of terracotta in high performance assemblies. So we had with Walter P. Moore and One-to-One Architecture and some other colleagues, Studio NYL, we sort of took this project while it was on hold in the geometry and said, hey, let's explore terracotta. You know, in this one, we're actually like pulling the ribbons apart from each other and doing some things that really weren't helpful for how you construct it, because it meant all the fittings would have to be unique and whatnot. But we did learn a lot about like forming of clay and what it would take. And what you see here are the actual project pieces that are being laid onto clay forms here. And, you know, interesting enough, the clay forms are what were needed to fire those, because anything else, you know, steel would even melt in those kilns at those temperatures. So, you know, looking at everything from like the complexity of like even like, okay, maybe that wasn't a good idea, you know, we had to, you know, it's feasible. We can pattern cut, you know, little pieces to fill in the ledges and the soffits. But, you know, I think a lot of this was in learning and just like the sort of like what happens when the plasma cutter goes down because someone is using the ceramics kiln and you can't fire up the plasma cutter because the breaker will break. In any event, these things happen in construction, right? Suddenly we're doing like these fittings that are like by hand that were just actually kind of almost impossible to do by hand. They were so unique. But going through all the motions, like really even looking at the building in solar and what are like potentials for like, you know, this is an early thought on evaporative cooling, you know, on those steps. If we're terracotta, and we looked at sort of like the color and the sort of thermal properties of terracotta. These are some readouts that we had inside the box, outside the box, you know, red, white, black terracotta. In the end, there wasn't much difference, but what was odd was there wasn't much variance from the internal to the external. And that's just, I think, from the fact that terracotta just has such a thermal mass to it that it almost acts like a buffer. So yeah, just like even real novel ideas. This guy from Walter P. Moore was like, yeah, what if we did this, you know? And so, you know, I think that in the end, what you might wonder is if you notice like a lot of the panelization here does not look like this. So this was the earliest rendition where you're sort of just taking horizontal slices through this thing like a wedding cake. And as you can see here, what that creates is a whole host of uniqueness, which was very difficult to deal with in metals or any material. You'd have like multiple extrusions, die sizes, whatnot. Here we're showing how, yeah, you would need actually 3 different dies in order to take care of 3 different angles. If they were all, yeah, they're all the same vertical height, but then, you know, it actually creates more uniqueness. And then we said, well, all of the base geometry is developable anyway. You can flatten it. So what if you take a grid, put it on the surface itself and sort of re-roll it? So, you know, if we're using just cylinders and planes as this drawing is showing, and this base surface can be unrolled or flattened, you can apply this texture and then re-roll it back up. And a lot of this was initially, yeah, just set out on a certain grid like this planter box. But everything you see up here was you know, someone on the team like really manually just crafting that, like making it look right, you know, and not making it look overt through the curves, really feathering that out. We got, you know, models from the fabricators that came back to us. We overlaid them with our models, right? Look for discrepancies. And, you know, in the end, just really everything just had to be pushed through and tested in sort of like shop drawings. And so this is the Walter P. Moore. This is the model that Kais's team actually developed and showing basically all of the members that are in here that aren't part of the primary system required just for the glazing
or the terracotta skin to exist. And you can see more of that here, And in the end, you get into like their full construction centerline model. When we got to construction, the construction team would take all these models, start overlaying them with their subcontractors' models, but all driven off of basically our models, right? And eventually what you see there in green is the actual steel model that the contractor had. This is just an overlay showing like out of all that secondary steel that we had, set out and intended to be there. The yellow is showing the moves, the purple is like the original position. So there was very little variance and deviation. And eventually you have like a high level construction model, this coming from the steel fabricator. Everything being sort of jigged up and tested in the digital workspace before you get to site. This is that stairway. You can see this sort of like slab underneath the precast risers running across there. This is before you get the waterproofing on there and whatnot. So, I'm going to blow through this last bit, but mock-ups and testing, this is super fun where we're doing constructs and testing out what is a curved framing assembly, what is a flat or planar assembly, and really kind of having the subcontractor test those out, and then into actual performance mock-ups where we're testing seismic and spraying this thing for water. Here you see the clips that we're holding on the terracotta, which actually we found leaks due to the green bits that were the thermal break. Just going through all the sort of testing, typically just using a fan from like a prop plane, prop engine, blowing water onto this thing, looking for infiltration. So all these things just continue into construction administration when we're on site, putting things on the wall, all these different sort of weird situations with the terracotta, and here, seeing a portion of the lobby where the pattern's completely gone vertical now, right? Those pieces had to be slip cast because they were so big. These pieces were special cases, right, where all the slivers you see everywhere, and basically just like working through the sort of fabrication. This is sort of them at the Boston Valley Terracotta doing QA/QC on the variances. So you very small, less than a 16th of an inch sort of variances, and then shop drawings, all the clips. Somebody's working out every single one of these clips in 3D. I can't stress how many people were involved to get any given project done, but this one especially. And just working out little problems. How do you install the glass here? This is a little pocket here on the side of the curtain wall. You'll see that they never even put the removable panel on there that we suggested. They felt that it was fine without. I think we probably okayed that. But everything down to even the nuts that were like kind of custom designed. All the interior is actually suspended on stud framing. So that's an interesting point, at what point it goes from stud framing to steel support. And basically, throughout all of this, the notion of like continuity, and even with the plaza, right, you see how there's this huge cavity underneath that is just like waterproof bathtub. And going through all the sort of different installation, field cutting was important. So what's interesting to note is every single one of these sort of edge cuts is in fact a field cut, and that was one of the ways that we got this thing under budget. Because number one, if you had these made in the shop, they probably wouldn't fit once you got out to site exactly where you wanted them. The notion of craft and somebody like being able to feather in all the sort of like anomalies and just massage those out was important. Just kind of getting to the end of it here, but just final, pictures of some of the construction. This is like that planter box. It's essentially one big truss that is just clad in that terracotta, completely flat, and then where we are right now, which is actually pretty pronounced, all the curvature that's going on this wall here as well as down low. I always joke how that looks like a fisheye lens, but in any event, that's it. And we have some time for questions, if you guys have questions. Yeah. Yeah.
So one of the earlier rendering picture that I see on the slide, I noticed that the sash have like horizontal, kind of like, which demonstrate that continuity that you mentioned, without having that break on the tile. So in reality, when you do construction, by breaking up into smaller pieces, was that the constraint of the material?
Yeah, I mean, what you see, the size of that panel is actually very thick. So at 2 inches, that's actually twice as thick as they normally come, right? And the reason for that was because we had an open joint, and we didn't want to see the clips so much. So if it was a little deeper, that was sort of driving the thickness. We're like, how thick can we get it? Because we want to bury the clip. And we wanted to get that, even though now the pattern swims all along, however the re-roll kind of made it go. Everything is kind of driven from, as far as the length, what is the largest piece, which was 5 foot, those are 12 foot tall, the big ones are 5 foot. And that's also by like what they can handle in the shop. Because when it's wet, it comes out of extruder. The 5 foot long piece is like 70 pounds dry. So like when it's wet, it's like over 100 pounds. The guy's trying to get it off the table, right? And like the minute you touch it, there's a thumbprint, right? So there's like a funny kind of really, everything to do with the terracotta is very difficult to control. It was even, everything you're saying, yes, right? Panel size, constraints, where it wasn't really a big deal. Like as far as like, how the panel attached, how it worked structurally was the same as a flat panel. It was just that we curved it, right? So as long as every single layer could be easily curved, it was like we knew it would work, right? What we didn't know so much, and was funny because like in the research, we actually did this to ourselves. Well, we took one surface, one like that, one like this, and then filleted it. But that never happens in the building. Right? So what we did was we created this twisted surface in the cylinder. The actual building here has no twisted surfaces. It's just cylindrical. So when we got the one slide where we see a design surface and then there's sort of like fabrication model, there's deviations because they didn't actually take a cylinder and offset it to get the inner surface. Like this is like a section, right? Because like when you put that in the oven, one side is like kind of uneven in tension than the other. And they're like, no, it's not going to work. It's not going to work. We're like, no, show us it won't work. There's like a lot of kind of tension about this because like it was a big surprise when we got that back. And we found that like each one of those panels is in fact a 2-rail sweep if you look at it in Rhino, right? It's 2 rails, but they take one section. That section, it's just a rectangle. And they sweep it, so it actually never curves. So like I think that's like without me, I mean, but that was these things kind of like play out in ways you don't think about, right? We're like, oh yeah, like this is a slam dunk, we got this all figured out, and then so I think that points to something about really listening to material, but also like the subs and being able to work with everyone on the team. Any other questions?
I have a question. So you talked about fabricating the panels. What was the formwork like? How did they create the formwork for each of these custom shapes? And what was the digital fabrication process like for creating that formwork?
Right. So they took our design surface model that had all the sort of center lines marked on them, center lines of the joints, right? Because from that in the detail, you can offset that center line and get like the joint sizes, and they can derive all their sort of 2D. So there's a whole process of that, and we had known them through the research, and I had we already had a bit of sort of working knowledge in their limitations and what they struggled with. So, yeah, as far as that geometry, once they got that, they would essentially develop their model. We would then take that back in, and so yeah, that process was kind of comfortable because they were always using our geometry. But yeah, I think that was the main thing. Yeah, I think Boston Valley Terracotta. I think the thing was that they were really geared to pushing technology, right? So the formwork for those kiln sort of molds, right? They were all actually initially just CNC milled out, and then they create slip casts of these things, or molds to then slip cast, and that's how they got the actual mold. Yeah, and then I think everything else is really craft, like everything from the process in terracotta. It's a beautiful thing of like the technology meeting crafts, right? Because like everything in the shop is like 7% bigger, like all the rulers, because like, everything shrinks in the kiln, and there's like this just really artisanal knowledge about that stuff. But the process was extrusion, right? Very automated. They set the machine up for the 5-foot thing, the 3-foot thing, It comes out onto the table. Before it gets put onto the mold, they're all the same panel. So they were essentially like just getting them, the ones that were flat, just cut the size. A little oversized because there's always a trimming thing after it gets fired. But as it comes out, it has a texture, this micro texture on the face already. And it has the cells to give it lightness and all that. And so I think, it was really kind of them, the digital process, and I think looking at the model and using their knowledge base of like how tight was too tight of a curve, and just like I think their empirical knowledge. But yeah, like how they use technology was very interesting. I mean, they even have a 3D wire cutter that can kind of rotate as this extruder thing goes through, and there's a lot of aspirations that they developed as far as how to integrate digital fabrication processes, right? Yeah. Okay.
So, because of the fabrication, all that, a lot of changes, I can tell that a lot of changes happened throughout the whole process. How do you communicate those changes to every single person that's involved in the process?
Yeah, I mean, I think in design you're working with a much tighter group, right? As it gets further into construction, it gets a little more complex. But definitely having that design surface model and a set of details that talk about each one of those systems is like fundamentally the first step. And I think there's enough sophistication throughout all the teams now, engineering and contracting, that like the model becomes really this point of reference. And depending on like how sophisticated that process becomes, as people take on responsibilities in the project, they'll be producing their own data set, right? Which then becomes pretty soon your design model stops being sort of like the active model in the mix, but it's the thing that is the DNA and sort of the constraint or what the construction team is contractually obligated to. So, and that goes to the contract documents like the drawings and the specs. And so it should be, in an ideal scenario, very explicit and very clear what they're doing, right? And then, as you say, like as you drill in, there's going to always be things that come up. But I think there's always that like desire to, best present the design. We use the word design intent a lot, right? But really, I think it's getting used to just saying it's the design, but it's just well vetted, It could just be, that's just the design, but you have like a whole slew of maybe research and data and well-vetted kind of documents as to what that is,
I think that makes it a real kind of design, and you know, that's the starting point then for when you're communicating things. But there are weekly meetings that go on with all this stuff, all the scope, you know. And the general contractor in construction will set up all these meetings and is responsible for coordinating that, you know. And then we as architects, we sort of just uphold the design documents in that process, really. So, yeah, once you issue those things, it marks a much different conversation. Yeah, yeah.
Thank you.
Mm-hmm.
I was just wondering if you knew anything about why for the majority, the walls and the ceilings never, or most of the walls never seem to touch the floor or the ceiling throughout the whole building.
Well, that's interesting. So I think a lot of, and this is kind of a lot of the detailing aesthetic of a company too, right? I mean, there might be some reasons for that, like lighting or this, that, the other. But I do think it is probably a language of complexity when you think about all these things coming together, right? Like how much it takes to get, say, like 5 different people to come together and make a corner. You know, like, I mean, like a lot of times you'll see a lot of the detailing here, and I know very much of this because, you know, I was much more focused on everything on the exterior, but you can see here the exterior comes in interfaces with the interior, and there's really no like separation, right? Form and skin, interior, exterior. But I think the main thing is a lot of times when there's just like chaos about to happen in an interface, and it's a very difficult interface, a lot of times it's better when there's no interface at all. So in a funny way, for that wall to come down and interface with all those, yeah, there are people that do that. Make a little sawtooth thing, bring the drywall down, you know. But I think this is very deliberate in sort of the way that systems are expressed as continuous and almost want to fly past one another. Other times they're very like taut, right? Like this wall in and of itself as the drywall system is very taut in how it resolves itself. Yeah, that ceiling is like, you know, a prime example, you know, like just having that reveal there allows you to have separation without really, and it's a lot less material, you know. If we design in a cove, that's like hundreds of feet of like aluminum. You can already see how much aluminum is here, right? Like almost on everything. So like the exterior detailing, we use the aluminum because that allowed us to hide that edge that was pretty clean, but they're just cutting it with a saw on site. I mean, that's actually, if I tell you this, I mean, this is like almost like outrageous that you would say, okay, it's cool to field cut that. You know, like this is a museum, you know, like you think like, yeah, this truck from 3,000 miles away, and it's like, you know, like super tight, and the guy goes up there and boom, it's in. But like, you know, things migrate. You know, I will tell you there are certain joints here probably. It'd be really cool to get like some goggles and see the, you know, the design model with the center lines and just see where they ended up. So yeah, that's a big reason for that. I mean, I think I fortunately worked at an office where they had a lot of design. I mean, like, yeah, like Tom Main, like what a privilege, you know. But there was years of approach kind of embedded into a language of, you know, stuff.
I was wondering that, did you have any specific art exhibit in mind when you were thinking about the intention of what was going to be displayed in the museum that you were designing?
Yeah. Oh yeah, for sure. No, I mean, I think that was like a much to the credit of like, you know, it's very difficult. You'll see as you go out into the real world and sort of having this decisiveness about early design and concept and schematic and just coming up with form and something that's like, you know, you've already thought about what would happen, like you're saying, what would happen in these spaces, you know, and like some of the renderings pointed to that, you know, the activating the public space for like more exhibition, kind of outdoor, kind of, they'll have fairs here, I think, little, sometimes even like people selling wares, performances, that whole upper wall kind of like that goes on here that opens up onto the plaza. It's meant to be kind of like this multi-use space over there.
I have to see if the nano wall survived, but there were 2 spaces that had a splitting mobile screen there. But the whole notion of kind of versatility in program, yeah, for sure. And I think also, that window gallery underneath the planter out there was a big deal too. The notion of kind of like this gesture to the public of kind of, echoing, like right on the door, everyone is welcome, it was a big deal that they got this museum to be free for like a few years, I think, several years, by one generous donor. But yeah, absolutely. That was, and then that goes by the way too of like, kind of like, okay, well, it's just the plaza. Well, that would probably be a failure right there. Right? We see in the 80s, all these like, the plazas that are in the cities that are just empty and barren and not used, right? So I think there was probably, a thought to how to make it really an integral part of like kind of the complex. Yeah. All right.
Thank you, Stan.
Well, thanks for having me, guys. Cheers.